In this class, we're going to review our first quiz. So we have 10 questions, and students are doing very well. I think the average is about 7 problems or 6 problems. So in this class, we're going to go over questions one by one. And there are a few fairly simple ones, and I will go fairly quickly. And there are a few that fairly challenging ones. I'm going to spend a little bit more time. And also, we're going to look at extensions of these problems. So just for you to think. So let's look at problem number 1. Question is, find a sequence and fill in blank. One, 4, 16, 64, 256, and blank, and 4096, and 16384. So for this question, one technique that you remember to find a pattern is taking a ratio of neighboring terms. So for example, if you're taking the second term divided by the first term, you see it's a 4. 16 divided by 4, it's a 4. 64 divided by 16 is a 4. So you kind of confirm that this is going to be a sequence that the ratio of the next term over the current term is a constant. Or that ratio you find out is 4. So basically, for this term, it's going to be 256 times 4, which is 1024. Okay. And you can verify by looking at 4096 divided by 1024 is again 4. So the pattern continues. A different way of looking at this question is the following. You recognize all those 4, 16, 64, 256 are powers of 2's. In fact, 1 is 2 to the power 0, 4 is 2 to the power 2, 16 is 2 to the power 4, 64 is 2 to the power 6, 256 is 2 to the power 8, and 4096 is 2 to the power 12. So what's the pattern here? You basically see the exponent of 2 to the power something are all the even numbers. 0, 2, 4, 6, 8. So here it should be 2 to the power 10. And this is 2 to the power 14. So that also confirms the pattern. A different way, of course, you recognize these are all powers of 4's. So 4 to the power 0, 4 to the power 1, 4 to the power 2, 4 to the power 3, 4 to the power 4, the blank, and 4 to the power 6. So clearly it should be 4 to the power 5. Of course, this sequence and this sequence are really the same sequence. That's it for problem number 1. Let's look at problem number 2. Again, it's a fill in blank question. The sequence goes 1, 1, 2, 3, 5, 8, 13, blank, 34, 55, and continues. So what's the value in the blank? Now remember that besides taking the ratio of a sequence, we also mentioned the first thing you should try is take a difference between the neighboring terms. So why don't we do that? Take the difference, let me call it a delta difference. So the second term minus the first term, it's a 1. It's a 0, sorry. And the third term minus second term is a 1. The fourth term minus the third term is a 1. 5 minus 3 is a 2. 8 minus 5 is a 3. 13 minus 8 is a 5. And we don't know. And the next one is, and this 55 minus 34 is a 21. And the other we don't know. So now look at this different sequence. And you see that sequence, again, you don't see any pattern. Now, remember that for an arithmetic sequence, the difference is a constant, right? This certainly is not. But there's something interesting happens. When you take the difference, you see the whole thing is actually, it's almost like the original sequence, just shifted by 1. The difference of that is the previous number. 1 is going to 2 is going there, 3 is that, 5 is this term. Okay? So what does that mean? It really means that when I'm taking the next term minus the current term equals the previous term. Okay? Again, you see 8 minus 5 equals a 3. 13 minus 8 is a 5. And here, 3 minus 2 is a 1. A different way of saying it is, if you take the previous two terms, adding up, it's going to be equal next term. 1 plus 2 equals 3. 2 plus 3 equals a 5. 3 plus 5 equals 8. 5 plus 8 equals a 13. So what's this term? It's going to be equal 8 plus 13. This plus this is going to be equal 21. And let's verify if that pattern satisfies. 13 plus 21 equals 34. 21 plus 34 equals 55. How about the next one? 34 plus 55, what's this term? It's going to be 89. What's the next term? It's 144, which is 55 plus 89, 144. Interestingly, this is a very famous sequence. It's called the Fibonacci sequence. The Fibonacci sequence is really the sequence. The first two terms are 1 and 1. After that, every next term equals the sum of the previous two terms. So the next term is going to be equals 1 plus 1 equals a 2. Next term is 1 plus 2 equals a 3. Next term is 2 plus 3 equals a 5. Next term equals 3 plus 5 is 8. And continues. This is one of the most famous sequences in mathematics. It actually also occurs a lot in nature. So for example, if you count the petals of a flower, the number of petals of a flowers, almost all are in the numbers of Fibonacci sequence. Either there are 3 petals, or 5 petals, or 8 petals, or 13 petals, and so on. And there is a reason for that. If you're interested, you can look up on Wikipedia or Google to find out this very mysterious but exciting fact. Now let's look at problem number 3. Problem number 3 is the following. The first 5 terms of a sequence of an arithmetic sequence. The first 5 terms of an arithmetic sequence. Are 6, 10, 14, 18, 22. What is the 21st term? Now, the first question is, what's an arithmetic sequence? We know an arithmetic sequence is you first give a number, and after that, the next term is going to be you adding a constant to get the next term. And for the next term is the current term plus a constant. It's always following that sequence, right? That's the arithmetic sequence. So a different way of writing it is you start with a number a, and if the difference is a d, the next term is a plus d, and the next term is a plus 2d, and a plus 3d, and so on. That's an arithmetic sequence. So really, we don't even need to specify 5 terms of a sequence. As long as you specify 2 terms of a sequence, and you know it's an arithmetic sequence, then if you're given 2 consecutive terms, you take the difference, you get that d. And if you're given the first number in the sequence, then you also have the a. Then you have everything determined. So let's look at what's the d here. So a is going to be 6 because that's the first term. A is 6. And the next term is basically a plus d, or if you take a difference between 10 and 6, you get a d. D equals 4. Right? So you see like the next term, the third term is 10 plus 4. It's always 4. D equals 4. So what is the 21st term? Now, some people will get that confused a little bit. Some will say a plus 21d is the 21st term. That's not correct. Because the first term, if you look at, is actually a, or rather a plus a 0d. That's the first term. Second term is a plus 1d. Third term is a plus 2d. So you see the number of term, the term index, and how many d's you have is always have a difference 1. In fact, this number is the term index minus 1. The 10th term, for example, is going to be a plus 9d. And for the 21st term, it's going to be a plus what d? It's 20d. Okay? For those students that sometimes are not sure about what this coefficient should be, you need to look back to check the first few terms to find the relationship between this coefficient and the term index. And once you're sure about that, you should be very confident of what this coefficient given any term index. Okay, so for here, a equals 6 and d equals 4, 20 times 4, and this is 86. And I choose 21 because I want to make this multiplication to be easy. I want to have a simple answer. Okay, now let's look at problem number 4. What is the largest integer whose square is less than 1 million? Okay, so what is the largest integer whose square is less than 1 million? So really we're asking what is the largest n, let's say n square is less than 1 million. Right? What's the n? What's the largest n such that this is still true? So the thing that you need to recognize is for 1 million, what number square is going to be equal to 1 million or as close as to 1 million? And the 1 million has 6 zeros. You realize that it's actually 1,000 square equals 1,000 times 1,000, which is 1 million. Okay, why that is true? Because we know that 1,000 is equal to 10 times 10 times 10. Every 10, you're going to adding a 0 to the integer. So 1,000 times 10 equals 10,000. 1,000 times 100 equals 100,000. 1,000 times 1,000 equals 1 million. So this is true. So really we're asking what's the largest n such that n squared is less than 1,000 squared. At this point, it should be very clear. Its n is going to be less than 1,000. So the answer, what's the largest n less than 1,000? And it is 999. Now, for those students that feel this question is too easy, let's change the question slightly. What is the largest integer whose cube is less than 1 million? Okay, and for cube, of course, is n to the cube is less than 1 million. Okay, what's the largest n? This is a question for you to think about. Problem number 5 is evaluate 1 plus 3 plus 5 plus 99. What is this? So for this, there are several ways of doing it. I'm going to describe, I guess, 2 ways. The first way, first recognize this is a sum of arithmetic sequence. And it's really the sum of all the odd numbers. 1 plus 3 plus 5 plus 7 plus all the way to 99. So one way is you recognize 1 plus 3 plus 5 plus 97 plus 99. Okay? I'm going to pair them together. 1 plus 99 is 100. 3 plus 97, okay, I'm putting 100. 3 plus 97 is a 100. 9 plus, there's a 95, is 100. Okay, so we're going to make a pair of 100. And why we can make all those pairs of 100? Because it is an arithmetic sequence, which means that they are, one number is increasing by the amount d, the other number is decreasing by the amount d, so that if you adding those pairs, the pair sum does not change. Okay, so here I'm going to adding a lot of 100s. Now the key question is, how many pairs? Let's see, number of pairs. Each pair is 100. The number of pairs. For the number of pairs, there are really 2 ways of thinking about it. One way is find how many numbers there are. 1, 3, 5, all the way to 99. How many numbers there are? Quick. Okay, these are all the odd numbers inside 100, and 1 to 100, there are 100 numbers, and even number and odd numbers basically have the same numbers, so it's 50. So if you have 50, number of pairs is 25, right? So it's 100 times 25. That's equal to 2,500. Okay? That's method number 1. Method number 2, I prefer slightly over the first method, is if I call this as S equals 1 plus 3 plus all the way to 97 plus 99, and I'm going to switch it. I'm switching the order of summation. Instead of from the smallest to the largest, I'm going to do the largest to the smallest. 99 plus 97 plus 95 plus all the way to 3 plus 1. And then I'm going to sum these 2 things together. S plus S, that's 2S, equals, now I'm adding 1 plus 3 all the way to 99, plus the 99 all the way to 1. But when I'm adding, I'm changing the order slightly. I'm going to adding those pairs first. And this is second pair, and this is third pair. This is the pair, and this is the last pair. All right? And because addition does not really matter which order you sum it up, right? Of course, I can do this. So 1 plus 99 equals 100, and plus 100, and plus 100, and so on, plus 100, and plus 100. And totally how many 100 there are? Now this is the total number of all numbers. It's 50 times 100. So the whole thing, 2s equals 50 times 100. So s equals 50 times 100 divided by 2 equals 50 times 50 equals 2500. Okay, that's the second method. It looks very similar to the first method, but why I prefer this one slightly over the first one is because the first one, when you do the pairing, if the number of numbers is even, then the pair is, you can really complete it. But if the number of the numbers in the sequence is odd, then you will have this very annoying fact in the middle. There's a number that is not going to be part of a pair. And then you have to handle it in a special way. And this sometimes you will forget about it, and then you get the wrong answer. In here, you don't have that issue. I'm just having the 2s and then sum up, and I don't have to worry about maybe there's a one element that's missing in the pair. So this is a slightly safer way. But for this, it's really the most interesting or striking fact of this sum is, for this, I'm adding all the odd numbers. It's always a square number. 1 plus 3 is 2 square. 1 plus 3 plus 5 is 3 square. 1 plus 3 plus 5 plus 7 is 4 square. 1 plus 3 plus 5 plus all the way to 99 is 50 square. Can you see the pattern of this 1 plus 3 plus all the way, let's say, 2n minus 1? What is this? It's always, when I'm adding all the consecutive odd numbers starting with 1, it's always a square number, which is equals n squared. And this is something that very interesting, and we have covered that in the class, and you probably should want to take a look. So now we come to problem number 6. There is a virus that splits itself into 2 copies in the next second. So you start with one virus. In second 1, in the next second, it becomes V and the V, where each copy will also split itself in the next second. This V will become VV, and this V will become VV. How many viruses will there be in 11 seconds? Now, some students confuse at in 11 seconds, what does it mean 11 seconds? In 1 second, you have 2 copy. In 2 seconds, you have 4 copy. In 0 second, you have 1 copy. And how about so this is 0 second, this is 1 second, this is 2 second, and how about in 3 seconds? Each V will split itself, VV, 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 and will be 8. So this will be in the 3rd second. The question is at 11 seconds, what is this number, right? So clearly this is really trying to find a pattern of this. At 0 second is 1, in 1 second is 2, in 2 seconds is 4. Clearly this is 2 to the power 11 for 11 seconds, or in n second, it will be 2 to the n. Okay, some people got it wrong that In the 11th second, he thought is 2 to the power 10. Now, again, for this kind of confusion, you need to go back to the first few seconds. For the first second, if you say 2 to the power 10, that means for the 1 second, you will think it's 2 to the power 0, but that's not the case, right? So you're always using the first few instances to check your answer, and that's very important. So problem number 6, the answer is 2 to the power 11, which is 2048. All right, now we get to problem number 7. Problem number 7, Alex read 10 pages on the first day. In the next 9 days, this is the first day. In the next 9 days, every day he reads 5 pages more than the previous day. So in here, you should recognize this is an arithmetic sequence. Every day she reads 5 pages more. So if the first day is 10, what's the second day? It's going to be 10 plus 5 is 15. How about the third day? It's going to be 20. Fourth day, it's going to be 25. Right? And how about in the 10th day? So first we're really asking, can you recognize the general formula? For the first day is 10, for the second day is 15, for the third day is 20, fourth day is 25. What's the 10th day? The question is how many pages he read in this 10 days period. So for arithmetic sequence, the 10th day is going to be equal the first term plus 9 times the difference, this constant in the arithmetic sequence, right? The D, which is every time I'm adding the D. In D here, it's very simple. It's a 5. D equals 5. So here the 10th element is going to be 10 plus 5 times 9. The 5 is the D, and the 9 is the 9th term. This is equals to 55. So really we're asking this question now, what's the sum of 10 plus 15 plus 20 plus all the way to 55? Okay? And here you can do this with pairing, or you can do the S of reversing order. In here, because there are 10 numbers, it does not really matter that much. So let's just do the pairing. 10 plus 55, that's a 65. 15 plus 50 is also 65. So there will be a bunch of 65s. How many 65 there are? Because there are totally 10 numbers. So in terms of pairing, you're going to have 5 pairs, because each pair has 2 numbers, right? So that's equals 325. That's the answer. Now we come to problem number 8. What is the unit digit of 3 to the power 2018? All right, so unit digit is the last digit. Let's see what's the unit digit. So 3 to the power 1, the unit digit is the 3. 3 to the power 2 is equals 9, so the unit digit is 9. How about 3 to the power 3? It's equal to 27, right? But the unit digit is a 7, okay? And you quickly see that this digit does not really matter, because 3 to the power 4, if I only care about unit digit, this 2 times the 3, this 2 is a 20. 20 times a 3 is always happening to the 10th digit or the 100 digits. It's only going to affect that. It will never affect the unit digit. So this thing, 3 to the power 4, only the unit digit only determined by 7 times 3, which is a 1. How about 3 to the power 5? the unit digit is going to be a 3. Okay, in here I'm actually should make it using a symbol not equal anymore. I just only care about unit digit. So let me put this kind of, it's a new equal, which means that the unit digit, 3, 5, the unit digit is a 3. 3 to the power 6, the unit digit is a 9. 3 to the power 7, the unit digit is 3 times 9, it's a 7. 3 to the power 8, the unit digit is going to be go back to 1. 3 times 7, it's a 1. Okay, so now you see, if I'm looking at the powers, if I'm making a table, power 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Power 1 is a 3. I'm talking about unit digit. This is the power. Unit digit is 3, and then it's 9, 7, 1. 3, 9, 7, and 1. 3, 7, 9, and 1. So clearly, you see the pattern here. The pattern goes every time when you go to a multiple of 4, when the power is multiple of 4, you go back to 1. Multiple of 4, you go back to 1. Multiple of 4, you go back to 1. So now the question is, 3 to the 2018 is going to equal 3 to the power 2016 times 3 squared. For the 3 to the 2016, this one is a multiple of 4. So this one is basically 3 to the power, it's a multiple of 4. So which means that unit digit, this guy will be a 1 times 9 equals a 9. Okay, that's a unit digit. By the same token, this question can be extended into the following. Will be slightly harder. What's the unit digit of, let's see, 7 to the power 2018? Unit digit. Okay, can you try this question? In fact, this question is not really harder than this question. It's about the same difficulty. Now let's look at problem number 9. Evaluate 1 plus 4 plus 4 squared plus all the way to 4 to the power 6. Okay, this is a sum of a geometric sequence, and we talk about this method in the class. S equals 1 plus 4 plus 4 squared plus all the way to the 4 to the power 6. You do this way. 4 times S equals 4 plus 4 squared plus 4 third plus to the power 4. This one goes to 4 to 6 and plus 4 to the 7. What I'm doing here, I'm basically multiplying by this constant ratio of this geometric sequence, 4 here. By multiplying by 4, I basically mapping the current term to the next term because they have the same ratio of a 4. So 1 times 4 equals next term. 4 times 4 equals the next term. Basically, 1 times 4 goes to this. 4 times 4 goes to the next term, right? 4 to the power 5 times 4 goes to 4 to the 6. 4 to the 6 to go 4 to 7. Next is another key step here. Now you have two equations. The second equation is multiplying by 4. The first equation is the original equation, s equals this. You take a difference, then equals 3s, because 4s minus s equals 3s. Now this whole thing is the following. 4 plus 4 squared plus 4 third plus 4 to the 6 plus 4 to the 7. This is the right side of the second equation, and minus the right side of the first equation. But because of the special property I did by multiplying 4, this term is the same as this term, so they cancel each other. This is the same term as this term. All the way cancel. 4 to the 6 cancel this one. Only left with 4 to the power 7 and the 1. So this equals 4 to the 7 minus 1. So the whole S equals 4 to the minus 7, 4 to the power 7 minus 1. Here I want to write as 4 minus 1. Just keep 4 minus 1 is 3. And so this sum equals 5, 4, 6, 1. Okay, so this is a technique I want you to really get really familiar. The sum of a geometric sequence, the common technique is multiply by that constant ratio. Finally, we come to problem number 10, which is probably the most difficult question of this test. If we know that 4 to the power n plus 4 to the power n equals 2 to the power 2019, what is n? Here, really the trick is the following. You first recognize I have two things, 4 power n plus 4 to the power n. This is the same as 2 times 4 to the power n. Yeah? Because that's really the definition of multiplication, right? 4 to the n plus 4 to the n, they are the same. So 2 times 4 to the n equals 2 to the power 2019. Because 2 times 4 to the n equals 2 to the power 2019, that means 4 to the n equals 2 to the power 2018. Because this is a 2 times 2, 2019 multiplied together. There's a 2 there, so I can divide by 2 by both sides, right? Correct? That's basic powers property, that 2 to the power something divided by 2 to the power another thing is just taking the powers, taking the difference of the powers. So now this is the equation. What's the n? In here, you can do two ways. One way is recognize 2 to the power 2018. This is really equals 4 to the power 1009. So 4 to the power n equals 4 to the power 109. Of course, n equals 1009. Okay, that's one way. You from the 2 and you convert to the power 4. The other way is from the 4 to come to the power 2. 4 equals 2 squared. So 4 to the power n equals 2 to the square to the power n, which equals 2 to the power 2n. Remember, when you have a to the power n to the power m equals a to the power n times m. And how you prove that is really a to the power n means a times a times a, n a's. N to the power m means that you duplicate that thing m times. So totally there will be m times n a's multiplied together, which is definition of a to the power n times m. So 4 to the power n equals 2 to the power 2n. So which means 4 to the power n equals 2018. This equals 2 to the power 2n equals 2 to the power 2018, which means 2n equals 2018, n equals 1009. Okay, this is, I agree this problem is slightly hard in this test, but we have many students solve these questions by themselves. So that's a great job. Okay, that's the explanation for all the 10 questions. Again, I want to congratulate students who did a very, very good job on this test. So keep up the good work.